All right, let's look at some vector applications. So vectors are nice because they're useful in representing things like velocity and force. And what makes them particularly useful is if there are two or more vectors that are acting simultaneously on an object, all we have to do to find the result is add the two vectors together and then analyze the resultant vector. That's kind of a mouthful, but we're going to do some examples here. Okay, so getting into analyzing these vectors first, let's just talk about an example of what this might look like. So let's say that you and your friend go to the river, right? And the river is flowing 5 miles per hour downstream, right? So already there's a vector measurement, right? We have a magnitude of 5 miles per hour and a direction of downstream. Now let's say that your friend jumps into the river in an inner tube. So here's your friend in an inner tube in the river, and your friend starts paddling downstream at 2 miles per hour. Now, if I were to ask you how fast does it appear your friend is traveling, well, the answer would entirely depend on your frame of reference, right? If you are in an inner tube in the river with your friend, then your friend appears to be traveling downstream at 2 miles per hour, right? Because you're both in the river together. So this 5 miles per hour is affecting both of you equally. And so all you observe is 2 miles per hour. But if instead you're on the shore over here observing this, you would see your friend traveling downstream at 7 miles per hour, right? We would just take the vector of the river, 5 miles per hour downstream, and the vector of your friend, 2 miles per hour downstream, and add them together to get 7 miles per hour. If, on the other hand, your friend started paddling upstream at 2 miles per hour, again, we would add the vectors together, but they're in opposite directions, right? So essentially, we could think of this as positive 2 miles per hour and negative 5 miles per hour, and the result would be negative 3 miles per hour or 3 miles per hour downstream. Now, all that's pretty intuitive, right? But let's say that your friend starts paddling toward the shore at 2 miles per hour. Now, if we're asked how fast does your friend appear to be paddling and in what direction, let's say that you're now in a tree above the river just looking down on the situation. Well, if the river is traveling at 5 miles per hour and your friend is paddling at 2 miles per hour, your friend is going to appear to move in this kind of direction in the river, right, at an angle. And the way that we arrive at what is that angle and what is that magnitude is by adding these two vectors together. So we're going to look at exactly how to do that, but we want to keep a couple things in mind here that we're looking at adding vectors, and our frame of reference is important, right? It depends on whether we're in the river with your friend or on the shore. So more on that when that comes up in this example. Let's go ahead and dive into the example. So what we're going to look at right now is an airplane problem. So this says a jet maintains a constant airspeed of 500 miles per hour due south. So let me write that down first. So a jet maintains a constant airspeed of 500 miles per hour due south. Okay. And then the second part says the jet stream, or in other words, the wind, the jet stream is 80 miles per hour north bearing 45 degrees east. So I'll write that down and then I'll explain what that is and what those directions are. So the jet stream is 80 miles per hour, and then we're going to write the direction like this: north 45 degrees east. All right, cool. Okay, so we have a couple of vectors here, but first let's break down this directionality, the directionality of this second vector here. So it's given to us as north bearing 45 degrees east. So this is what's called a cardinal direction, right? The north, east, south, west directions are cardinal directions. And the way that we observe these, or the way that we describe these, so we have north, east, south, and west, is like this. When we look at this, this is giving us first the primary direction of travel. So this is, when it comes to the four directions, we want to look at what is the dominant direction being traveled. That goes first. And then this part here, the degrees and the second direction, they kind of fit together. So this is giving us the secondary direction, or we can think of it as the offset, right? So there's the offset. And the way that we read this is the primary direction comes first. So this one says that we're primarily traveling north, but there's a 45-degree offset toward the east. In other words, we start by going north, but then we move off 45 degrees here, and the direction of travel is actually this. So it's a northeastern travel, right? So it's mostly north, but 45 degrees to the east. Now, this one's a little bit ambiguous, right? Because 45 degrees is right in the middle. So number one, we will never get a number larger than 45 degrees, because if it were going to be larger than 45 degrees, then actually the primary direction would just switch. But let's look at something that's maybe a little less ambiguous. Let's say that we're given something that's west bearing 20 degrees south. Well, the way that we would do that is we would say the primary direction is toward the west, so we're mostly going west, but there's a 20-degree offset toward the south. So that direction of travel would look like this. Now, the direction that is actually being traveled is the direction that this arrow is pointing, right? But the way we describe it is west with a 20-degree offset toward the south. Right, so that's what a cardinal direction is. That's how we describe those. Now, we're going to look at a little bit later how this relates to the unit circle. And essentially, what we're going to be doing with these vectors is we're going to find the unit circle angle, right? So I'll find the unit circle angle first, and then we're going to translate that into a cardinal direction. So more on that when we get there, but let's just keep these ideas in mind. Oops, let me get this stuff out of here so we've got some room to work. All right, so we'll come back to this in just a second. First thing we want to do, anytime we're adding vectors together, we want to first break them down into their components, each one of them, and then add the i's, add the j's, and observe the resultant vector. So those are going to be our steps. First, we want to break down each of these vectors into their I and j components. So the first thing that we're going to look at is our first task here. So we'll say, number one, what we're going to be asked to do is to express the velocity of the jet relative to the air. So that's our first objective. So express the velocity of the jet relative to the air. And we're just going to call this, let's see, relative to the air. Let's just call this VJ. That's going to stand for the velocity of the jet. All right, so the way that we would find this is, let's look at that vector information that we're given. So this tells us that the jet maintains a constant airspeed of 500 miles per hour due south. Now, the reason that I highlight airspeed here is this is giving us our frame of reference, right? So it's saying the jet flying in the air is 500 miles per hour due south. So this is just like your friend paddling in the river, right? So the frame of reference is in the river, you're looking at your friend paddling. So in this case, we're in the air watching the jet fly. And so it's 500 miles per hour due south. So I'm just going to sketch a little diagram of that. I find sketches very, very useful. I definitely recommend them. So if I think about a jet flying 500 miles per hour due south, well, we're just going to have a straight line down south, right, down in this direction. And the magnitude of this line is going to be 500 miles per hour. So this is 500 miles per hour due south. Now, I want to think about this in terms of a vector. So this is going to be VJ, right? So the vector that describes the movement of the jet is going to be equal to, and if we look at this, we're just going to think about this as our unit circle. So 0 degrees, 90 degrees, 180, and so on, right? So we could say, oh, it's a 270-degree angle, or we could just look at this and say it's not going left or right, so there's 0i. It's going straight down, so all of that is negative 500j. Boom, there's our vector for the jet. So I'm just going to, let's see, let me just cut this out here because we're going to need that later. And we'll save that for later and get rid of that. Okay, so there's that. Let me just set this aside. And let's look at what's next. So the first thing we did is found the velocity of the jet. Now, step 2, we want to express the velocity of the jet stream relative to the ground. So number 2, express the velocity of the jet stream relative to the ground. All right, we'll call this VJ for V ground. Okay, so this is essentially saying express the velocity of the wind, the vector of the wind, relative to the ground. So this is kind of like if now so relative to the ground means that's our frame of reference. So we're standing on the ground and we're watching the wind blow, right? So this is kind of equivalent to if you're standing on the shore watching the river flow. So we're going to call VG. We want to find the I and J components. And again, if we go to a diagram, so we have this over here, and this is telling us that the wind is blowing in a northeasterly direction. So north bearing 45 degrees east, or exactly like this. So there's a 45-degree angle there, which also means that this is a 45-degree angle like that. And the magnitude is 80 miles per hour. So to find the I and the J components, I'm just going to use our vector formula that says that VG is going to be equal to the magnitude, so 80 miles per hour, times the directional information. So the cosine of 45 degrees for I plus the sine of 45 degrees for J. And then we'll just solve this, right? So we get VG is equal to 80 times root 2 over 2I plus root 2 over 2J. And then we'll simplify. So here we go. VG is equal to 40 root 2I plus 40 root 2J. All right, so there's the vector of the wind relative to the ground. So there's that, and now I'm just going to cut this out and put it over here with our other vector. So now we know the velocity of the jet in the air, and we know the velocity of the air relative to the ground. So for this next part, we're going to be asked to find the velocity of the jet relative to the ground. So part 3, find the velocity of the jet relative to the ground. And we'll call this, I probably should, well, velocity, I guess R, because I don't know why, because relative doesn't make sense. Doesn't matter what we call them. Okay, so the velocity of the jet relative to the ground. If we think about how we get that, well, this is similar to you standing on the shore watching your friend in the river, right? So the way that we get that result is by adding those two vectors together. That's exactly what we're going to do here. We're going to say that the velocity of the jet in the air is the jet flying in the air. And then however the air is blowing the jet, that's another vector. And so when we add those together, we get the result of what the jet looks like from the ground. So let's look at how to do that. So what we're calling VR is just going to be these two vectors added together. So we add the I components together. So 0 plus 40 root 2 is 40 root 2I. Plus, and then we add the J stuff together. So we'll have 40 root 2 minus 500 in parentheses, and then J, right? So this is the resultant velocity. This is the resultant vector. So this is like you in the tree looking at your friend in the river swimming at a diagonal. Same thing here, but it's a jet in air being blown around. So this accounts for all of that, the jet in the air and then the air blowing on the jet. All right, cool. So there's our vector. Now what we're going to do is step 4 is going to ask us to find the magnitude of this vector and to find the direction of the vector. So we'll see a picture of this all together at the end of this. To dive in, let's go ahead and let's just start by finding the velocity, or excuse me, the magnitude of this vector. So we can say that the magnitude is equal to the square root of the I component squared, so 40 root 2 squared, plus the J component squared, so 40 root 2 minus 500 squared. And now here you're going to need a calculator, and you want to be careful of your order of operations. What I would do is 40 root 2 minus 500, get an answer, square that. And then separately do 40 root 2 squared, add it to what you got here, and then take the square root. If you do all of that, you get something that's approximately 447 miles per hour. So that's how fast the jet looks like it's flying, which kind of makes sense, right? If it's flying due south at 500 miles per hour, but the wind is pushing back up against it, primarily north with a 45-degree offset to the east, then it's going to kind of slow the jet down a little bit, right? The two vectors are opposing each other. So that's the magnitude of the jet. Now, to find the direction of the jet, we're just going to use our directional tools. So what I like to do with this is first sketch the situation so we have an idea of the direction so we can properly interpret the answer that we get. So here's what I mean by that. So I'm going to look at this and I'm going to say, all right, well, first thing I want to do is kind of sketch this vector right here. And it doesn't have to be super accurate. We just have to know a couple key things. So number one, we need to know, is the I component positive or negative, right? So in this case, it's 40 root 2, so it's positive. So I'm just going to sketch that over here. 40 root 2 is going to look, that's too crazy. I'm just going to sketch this like this. So yeah, let's just, boom, there it is. And I'm just going to label that 40 root 2. And now for the j component, I want to know, is this positive or negative? So looking at this, 40 times the square root of 2, I don't know what that is, but I do know that the square root of 2 is less than regular 2, and 40 times 2 is 80. Minus 500 is definitely going to be a negative number. So all I need to know is that it is a negative number. So I'm going to sketch it like that, and then I'll just label it what it is, 40 root 2 minus 500. Now when we do this, it's always an I and a j component, so there's always going to form a right triangle here. And then when we sketch the resultant vector, right, so from the original starting point to the final terminal point, it's going to look something like this. And and we solve for the magnitude, so we know that's going to be 447, but that's not super important right here. What's important here is we want to find this angle. We want to find that angle right there. That's our missing angle, right? It's always, once we sketch I and then j, and then our resultant vector, it's always going to be the angle that's attached to the origin. So how do we solve this? Well, we're going to just use a tangent function, right? Because we have an opposite side and an adjacent side. So we can say the tangent of theta equals 40 root 2 minus 500, so the opposite side, divided by the adjacent side, 40 root 2. And again, we want to be careful of order of operations here. Do 40 root 2 minus 500, get an answer, get 40 root 2, an answer, divide those two to simplify. And then we're going to take the inverse tangent of that result. So I'm going to have theta is equal to the inverse tangent of 40 root 2 minus 500 all over 40 root 2. And then we plug that into the calculator. We get something that says theta is approximately equal to negative 82.7 degrees. Right? It makes sense that it's a negative because we're in quadrant 4. Now we want to know how to interpret this. Well, if this angle right here is 82.7 degrees, or negative 82.7 because it's being subtracted from 360, well, that means that the primary direction of travel is actually this angle right here. Right, it's actually that angle. And how do we find that? Well, this whole thing is 90 degrees. So 90 minus 82.7 degrees means that this angle is about, let's say, 7.3 degrees. Right, so that's about a 7.3 degree angle. So when we express this direction, we're going to go back to our north, east, south, west. And we'll think about this is 7.3 degrees. So it's primarily south, bearing 7.3 degrees east. And that is our final answer. So this jet is flying at about 447 miles per hour, south, bearing 7.3 degrees east. Cool. That's it. That's the example. The rest of them in the book work a lot like this one. But if you have any questions, definitely come see me at CATS or after school. And yeah, be happy to help. Thanks.